This conference will now be recorded.
Good afternoon, students. Last class I explained this Kalman's method of finite side slope stability analysis. This is an important analysis method. Kalman's method is the first mathematical approach for the stability analysis of finite side slope. A very important method in Unit 2. Definitely for your examination point of view, this Kalman's method is an important concept. So in the today's class, I will explain this Kalman's method briefly. Please go through that procedure in the Kalman's method. So for the stability analysis of finite side slopes, we are using this Kalman's procedure. Now check that Kalman's method of stability analysis of finite side slope. So this is the diagram. So this is the finite side slope of embankment AB. So please everyone check this diagram. It is also prepared in the graph sheet. So please everyone follow this procedure. First, we prepare this embankment plan on the graph sheet with this side slope according to convenient scale. 1 centimeter is equal to some 10 meters or 20 meters scale. First, prepare this plan of the embankment or the canal or the earth dam on the graph sheet. This plan is having this side slope AB. This side slope AB is a finite side slope. Let this finite side slope AB with horizontal making the angle I. This is a known value. So this angle I is known value. With horizontal, the finite side slope is making the angle I. Then with vertical, this finite side slope making the angle 90 minus I. Take h is the height of the finite side slope, vertical height of the finite side slope. In the Kalman's method, we are going to discuss what is this maximum height of this finite side slope. What is the maximum height of this finite side slope so that the finite side slope is stable. So that is the main concept in Kalman's method. What is this maximum height of the finite side slope so that the side slope is stable. And during this embankment construction or the earth dam construction, we use the soil material. This soil material is collected from the borrow area. At that borrow area, by conducting subsoil exploration, we can calculate the density of this soil, gamma. We can calculate the angle of shearing resistance of soil phi. So by conducting the subsoil exploration at the borrow area, we can find out this density of the soil in the borrow area, and also we can calculate the angle of internal friction phi of this soil in the borrow area. Now coming to this Kalman's procedure. Just now I explained in the Kalman's procedure, we are going to discuss the maximum height of this side slope. What is the equation to find out this maximum height of the side slope? To prepare the equation of this maximum height in the graph sheet, first consider the failure surface AD. Draw this failure surface in the graph sheet, making some angle alpha with the horizontal. This is variable angle. So making some angle alpha, first draw this failure surface AD. It is a plane failure surface indicating the wedge failure. In the graph sheet, measure this length of the failure surface AD. Measure the length of this failure surface. So in this diagram, we know this length of the failure surface AD, and also we know this angle I in the graph sheet. Now to find out this maximum height of the side slope, first calculate the weight of this soil wedge in this portion ABD. The weight of this portion of soil ABD is called soil wedge. Find out the weight of the soil wedge W. Last class I explained in this diagram, cos 90 minus I is equal to H divided by AB. That is cos 90 minus I. Adjacent side H divided by hypotenuse AB. So the length AB is equal to H divided by this cos 90 minus I is sin I. So sin I is equal to H by AB. So AB is equal to h divided by sin I. That is this length AB. Find out this area of the triangle ABD, isosceles triangle ABD. At corner A, this angle. At corner A, this angle is I minus alpha. So the area of the triangle ABD is equal to half into length AB into length AD into sine I minus alpha. That is the area of this triangle ABD. So calculate area of this triangle ABD and consider unit thickness in the perpendicular direction. Then the volume of this soil wedge is the area into unit thickness. In the borrow area, we know this gamma, the weight of the unit weight of the soil. So multiply that volume with the unit weight, you will get the weight of the soil wedge W. W is equal to the unit weight gamma into volume of the soil wedge. Volume of the soil wedge is equal to half into this AB length. We calculate AB length is h by sin alpha sin I. So this volume of the soil wedge is half into h by sin I into length L into unit thickness, and the weight W is equal to gamma, that is unit weight, into half into h by sin I into length L into the unit thickness. But you know that 1 by sin I is cosecant I. So this weight W is equal to half into gamma into h into L into cosecant I. That is this weight W. So by knowing this I value, by knowing the bulk unit weight gamma, by knowing this height h, and by knowing this length L, we can calculate the weight W of the soil wedge. The direction is vertically downward direction. So we know the magnitude of weight W, direction of weight W. Weight is a gravitational force. Then check this diagram. At the instant of failure, this soil wedge is moving in downward direction. When it is moving in downward direction, the soil wedge applies the force Cm on this failure surface AD. Check this force Cm. This force Cm is parallel to surface AD. It is acting along the failure surface AD. We call this Cm as the mobilized cohesion. The Cm is called the mobilized cohesion force of the soil wedge on the failure surface AD. This is unknown magnitude. We know only the direction. The direction is parallel to surface AD. Since surface AD with horizontal making the angle alpha, this Cm also with horizontal makes the angle alpha. This is the second force in the diagram. First force is gravitational force W. Second force is the mobilized cohesion force Cm. Third force is in the failure condition, the soil wedge is moving along the surface AD only. The soil wedge is not moving in the direction perpendicular to perpendicular to the failure surface AD. Since this soil wedge is not moving perpendicular to surface AD, the surface AD applies the reaction force R on this soil wedge. So there is a reaction force acting on this soil wedge from the surface AD. That reaction force is acting in the upward direction, and with this perpendicular line, this dotted line is perpendicular to failure surface AD. With this perpendicular line, this R force, reaction force, is making some angle that is called phi m. This phi m is equal to mobilized angle of shearing resistance. We call this phi m as the mobilized angle of shearing resistance. So here we don't know the magnitude of reaction R. We know only the direction. The direction of reaction R is upward. With this perpendicular line, this reaction force R is making the angle phi m. We know this value of phi m. This phi m is equal to, in the borrow area, we calculate the angle of shearing resistance of this soil, that is called phi in the natural condition. Divide that phi value with factor of safety 2 or 3. You will get this phi m value. Phi m is called the angle of mobilized friction shearing resistance, that is equal to this soil angle of friction in the borrow area divided by factor of safety. So this phi m value is known. When this phi m value is known, we know this direction of reaction force R. With this particular direction, this reaction is making the angle phi m. So in this diagram, we have the soil wedge between the soil slope AB and the failure surface AD. In this diagram, we have the gravitational force, first force. The magnitude is known, the direction is known. The second force is Cm. This is the force applied by soil wedge on the failure surface AD. We know the direction, it is a downward direction, making the angle alpha with horizontal. Then the third force is the reaction force, unknown magnitude. We know the direction upward. With this particular line, this R is making the angle phi m. So coming to this Kalman's derivation for maximum height of the soil slope. Maximum height of the soil slope derivation in the Kalman's method. So first we calculate the weight of the soil wedge. The area is equal to half into length AB into length AD into sin I minus alpha. Length AB is h by sin I. So this weight of the soil wedge W is equal to half into gamma unit weight into failure surface length AD is L into h into cosecant I, h by sin I. 1 by sin I is cosecant I into sin I minus alpha. This is the weight of the soil wedge. So by using this equation, we can calculate this weight W of that soil wedge ABD in the discussion. Then the second one is the mobilized cohesion force acting on the surface AD Cm. This is called the total mobilized cohesion force. Then you can write this mobilized cohesion force as small cm into length AD. The small cm is called the mobilized cohesion force per unit length. So this total mobilized cohesion cm is equal to the cohesion per unit length small cm into length of the surface ADL. That is the equation of this capital Cm, the mobilized cohesion force. Please check this Cm force. It is applied by the soil wedge on the surface AD. Now coming to the free body diagram of the only soil wedge. So I am preparing the free body diagram of this soil wedge. In the free body diagram, we must indicate the force acting on the free body. So check the force acting on this soil wedge. First force is the weight of the soil wedge W. It is a known force. Second force is the mobilized cohesion. In the first diagram, we indicate the force applied by the soil wedge on the failure surface AD. That is the mobilized cohesion force Cm in the downward direction. That is the force applied by the soil wedge on the failure surface AD. According to Newton's formula, this surface AD applies the same force on the soil wedge but in the opposite direction. So here this Cm, the mobilized cohesion force, is the force applied by the failure surface AD on the soil wedge. It is acting in the upward direction parallel to the surface AD. So we know the direction of Cm, but we don't know the magnitude of this Cm force. Magnitude is unknown, only the direction is known. Then the third force is the reaction force. From this failure surface AD, the reaction force is acting on the soil wedge. The reaction force R. Just a minute, please. So from this failure surface AD, the reaction force R is acting on the soil wedge. You know that with this particular line, the reaction force is making the angle phi m. This value is known. Since this value is known, we know this direction of the reaction force, but the magnitude is unknown. So here this soil wedge is subjected to three forces, W, Cm and R. Out of these three forces, we know only one force in the direction as well as the magnitude. Then the remaining two forces are known, only the directions, not the magnitudes. We know the direction of Cm, not the magnitude. We know the direction of R, not the magnitude. But due to these three forces, the soil wedge is in equilibrium condition, just about to failure. So due to those three forces, The soil wedge is in equilibrium condition. So if the three forces keeps the body in equilibrium condition, those three forces will form the force triangle. That is the condition from engineering mechanics. So these three forces W, Cm and R, they forms the force triangle because these three forces keeping the soil wedge is in equilibrium condition. Check that force triangle by the three forces W, Cm and reaction R. This is the force triangle. First, prepare the vertical line on the white paper according to convenient scale. 1 centimeter is equal to 5 newtons or 5 kilonewtons. We know this magnitude of W. For example, if the magnitude of W is 50 kilonewtons, take the scale 1 centimeter is equal to 5 kilonewton, then this vertical line length is 10 centimeters. This 10 centimeter vertical line indicates the W. This is downward arrow direction. This is called the starting point. This is called the ending point. From that starting point of this weight W, draw a straight line parallel to direction of Cm. Here we don't know the magnitude of Cm, but you know the direction. So draw a straight line parallel to direction of Cm. Similarly, from this other point, this is called ending point. Draw the another straight line parallel to direction of reaction R. This is the reaction force. Only the direction known, not the magnitude. This is the Cm force. Only the direction is known, not the magnitude. So from this starting point, draw a straight line on the white paper parallel to force Cm, and from this point draw a straight line on the white paper parallel to reaction R. These two straight lines will meet with each other at this point. This is the common point, common intersection. Measure this length Cm on the white paper. If this length Cm is say 3 centimeters, in this diagram the scale is 1 centimeter is equal to 5 kilonewton. If this length is 3 centimeter, then this Cm force magnitude is equal to 3 into 5, 15 kilonewtons. And if the another straight line length is say 12 centimeters, then this reaction force magnitude is 12 into 3, 36 kilonewtons. So like that, on the white paper, prepare this force triangle having this weight W and Cm force R and reaction R. From this force triangle, we can calculate this magnitude of force Cm. We know that this Cm, force Cm is equal to small cm into length of the failure surface ADL. In the graph sheet, we know that length L of the failure surface AD. And from this force triangle, we know this magnitude of force Cm. Divide this force Cm with the length of failure surface ADL. Divide this force Cm with that length L, you will get the unit mobilized coefficient in this Kalman's method, small cm. Small cm is equal to capital Cm divided by length L. Now coming to these angles, last class I explained between the force Cm and weight W, this angle is 90 minus alpha. Between the force Cm and reaction R, this angle is 90 plus phi m. And between the force W and force R, this angle is alpha minus phi. These are the angles in that force triangle. Apply the sine rule in this force triangle. Cm divided by sine alpha minus phi m is equal to W divided by sine 90 plus phi m. So apply the cosine rule in that force triangle. Cm divided by sine alpha minus phi m is equal to W by sine 90 plus phi m. This is the Kalman's procedure to find out the maximum height of the soil slope AB. So in that force triangle, apply this sine rule. Cm by sine alpha minus phi m, W by sine 90 plus phi m. Sine 90 plus phi m is cos phi m. Bring this W to the left side and this sine alpha minus phi m to the right side. This equation becomes as Cm by W. Cm by W is equal to sine alpha minus phi m by cos phi m. So check that procedure carefully. So here we are using the sine rule in that forced triangle. So we got this equation. Cm by W is equal to sine alpha minus phi m by cos phi m. But you know that this total mobilized quotient capital Cm is equal to small cm into length L. L is the length of the failure surface AD. Cm is the mobilized quotient per unit length, Cm into L, divided by, we know this equation of W in the Kalman's method, half into gamma L H into cosecant I into sine I minus alpha is equal to, the right hand side is as it is. The right hand side is as it is, sine alpha minus phi m by cos phi m. Then simplify this left hand side, cancel this L on the left hand side first. Cancel that length L on the left hand side. Then on the left hand side, keep only Cm by gamma h. Cancel this L on the left hand side and keep only Cm by gamma h on the left hand side. Then that left hand side becomes as, the left hand side becomes as Cm by gamma h. Then bring the remaining terms to the right side. We already cancelled this L. So the remaining terms are half into cosecant I into sine I minus alpha. Bring them to the right side. And here on the right side, 1 by cos phi m is secant phi m. So keep this Cm by gamma h on the left side. Bring the remaining terms to the right side. This right side now becomes as, the right side now becomes as half into cosecant I. This is from the left side, cosecant I into sine I minus alpha into sine alpha minus phi m into 1 by cos phi m is secant phi m, equation 4. So in the Kalman's procedure, we got this small cm by gamma h equation. Small cm is the mobilized quotient per unit length. Gamma is the unit weight of soil. H is the height of the soil slope. Cm by gamma h is equal to half into cosecant I into sine alpha minus I minus alpha into sine alpha minus phi m into secant phi m. Now in this equation 4, in this Kalman's equation 4, this ratio Cm by gamma h is called the stability number. That is, in the Kalman's procedure, Cm by gamma h, by substituting, please listen everyone, by substituting the units of Cm, the unit of Cm is Newton per meter square. That is the unit of this Cm. Gamma Newton per meter cube into height h meters. So in the denominator, Newton per meter cube into meter, it becomes as Newton per meter square. In the numerator, it is also Newton per meter square. When the units are cancelled, this is a pure number. Cm by gamma h is a pure number. That is called the stability number of the finite soil slope. This ratio Cm by gamma h is a dimensionless number. There is no dimensions of this Cm by gamma h. It is totally a dimensionless number. Since it is a dimensionless number, we are calling it as the stability number, indicated as Sn. So in the equation 4, this left hand side Cm by gamma h is a dimensionless number. It is called stability number Sn. So the equation 4 becomes as Sn is equal to Cm by gamma h, that is equal to half into cosecant I. I is constant. It is the angle made by side slope with horizontal. I is constant into sine I minus alpha into sine alpha minus phi m. Phi m is also constant into secant phi m. So check this equation 5. In the equation 5, on the right hand side, only the variable is alpha. Alpha is the angle made by failure surface with horizontal. So this variable on the right hand side is alpha. So this stability number depending on this angle alpha. Since Sn stability number depending on this angle alpha, the stability number is maximum when dsn by d alpha is 0. Because the stability number depending on the angle alpha, the stability number is maximum when dsn by d alpha is 0. So differentiate this equation 5 with d alpha, with alpha, for the maximum value of stability number. So we are going to differentiate this equation 5 with alpha for this maximum value of stability number dsn by d alpha is 0. So dsn by d alpha is equal to d by d alpha of, we know this Sn value, half into cosecant I into secant I minus alpha into sine I minus alpha into sine alpha minus phi m into secant phi m. In this expression, half is constant, cosecant I is constant, and secant phi m is also constant. So in that expression, these three are constants. I is constant, so cosecant I is constant, phi m is constant, secant phi m is constant. So take them outside the differentiation. So this differentiation is half into cosecant I into secant phi m into d by d alpha of sin I minus alpha into sin alpha minus phi m equal to 0. These three are constants, they won't be 0. So only this d by d alpha of sin I minus alpha sin alpha minus phi m equal to 0. From this equation, we will get this expression. Then differentiate this equation with respect to alpha. It is d by d alpha of sin I minus alpha into sin alpha minus phi m. It is d by dx of uv form. D by dx of uv is equal to v into du by dx plus u into dv by dx. Apply that formula here. So in this equation, it is sin I minus alpha into d by d alpha of sin alpha minus phi m, that is equal to cos alpha minus phi m, minus the second term sin alpha minus phi m into d by d alpha of sin I minus alpha. Check that carefully. Sin I minus alpha, that is d by d alpha of sin I minus alpha, that is equal to d by d alpha of sin I minus alpha is equal to cos alpha. Just a minute, please. 1 minute. Wait for 1. So please everyone check this second differentiation. So the first differentiation, sin I minus alpha into d by d alpha of sin alpha minus phi m, that is cos alpha minus phi m. Then the second term actually plus sin alpha minus phi m into d by d alpha of sin alpha I minus alpha. Now in that second term, d by d alpha of sin I minus alpha is cos I minus alpha into d by d alpha of I minus alpha. But I is constant. Since I is constant, this is d by d alpha of I minus alpha. So it becomes as minus 1. So here we have minus 1. That minus into plus becomes minus. So this is the final differentiation of this d by d alpha of sin I minus alpha into sin alpha minus phi m. So from this differentiation, you will get this final form. So here sin I minus alpha cos alpha minus phi m minus sin alpha minus phi m into cos I minus alpha equal to 0. Bring this term to the right side. Bring this term to the right side. This equation becomes as, bring this term to the right side. That equation becomes as sin I minus alpha into cos alpha minus phi m, that is the left side. Sin I minus alpha into cos alpha minus phi m is equal to the right hand side Sin alpha minus phi m into cos I minus alpha. I minus alpha. Bring this cos I minus alpha to the left side. Bring this cos alpha minus phi m to the right side. Now this equation changes as sin I minus alpha divided by cos alpha I minus alpha. Sin I minus alpha by cos I minus alpha is equal to sin alpha minus phi m by cos alpha minus phi m. We got this equation. Please remember, we got this equation from dsn by d alpha equal to 0. That is the condition for the maximum stability number. The stability number Sn is maximum when dsn by d alpha 0. From that we got this equation. Simplify this equation. The left hand side sin by cos tan I minus alpha. Right hand side sin by cos tan alpha minus phi m. So simplify this equation. You will get it as tan I minus alpha is equal to tan alpha minus phi m. So from this equation, you will get the result as I minus alpha is equal to alpha minus phi m. Bring this minus alpha to the right side, plus alpha, minus phi m to the left side, plus phi m. So this equation becomes as 2 alpha is equal to 2 alpha is equal to I plus phi m. 2 alpha is equal to I plus phi m. From that, alpha is equal to I plus phi m by 2. So from this you will get alpha is equal to I plus phi m by 2. This is the value of alpha at maximum stability number, that is called the critical angle of failure slopes with horizontal alpha c. So from this equation 6, you will get that maximum, you will get this angle alpha is equal to I plus phi m by 2. We call that alpha at maximum stability number as the critical angle of failure surface with horizontal alpha c. So alpha c is equal to I plus phi m by 2. When the stability number is maximum, this is the value of alpha. Now to find out that maximum stability number Sn, substitute this value of alpha in the equation 4. Just now in this discussion, we prepare that equation 4 for the stability number. In that equation 4, substitute this value of alpha so that the stability number becomes maximum. So substitute that equation in the stability number, equation 4, the stability number is equal to Cm by gamma h. The stability number is maximum when alpha is equal to I plus phi m by 2. Since the stability number is Cm by gamma h, this Cm by gamma h is the stability number. So this Cm by gamma h is maximum when this alpha is equal to I plus phi m by 2. Substitute that in the right hand side alpha value. So this equation becomes as, the right hand side becomes as half into cosecant I into secant phi m, half into cosecant I into secant phi m into, actually it is sin I minus alpha, but this maximum is happened at alpha is equal to I plus phi m by 2. So substitute that here I plus phi m by 2 in this right hand side. Then the second term is sin alpha minus phi m. So in the equation 5, Sn is equal to half into cosecant I secant phi m into sin I minus alpha into sin alpha minus phi m. That is Sn stability number is maximum. The stability number is maximum at alpha is equal to I plus, at alpha is equal to I plus phi m by 2. Substitute that alpha value here. So the stability number is maximum. Stability number is Cm by gamma h. So Cm by gamma h into Cm by gamma h maximum is equal to half into cosecant I into secant phi m into sin I minus alpha is I plus phi m by 2 into sin alpha minus phi m I plus phi m by 2. Simplify these two terms on the right hand side. Take this 2 LCM in the first term. When I take this 2 as LCM, in the numerator it is 2i minus I minus phi m. 2i minus I is I minus phi m. This is the first term. So here this right hand side half into cosecant I into secant phi m into sin I minus phi m by 2. This is the simplification. And in the second term, take this 2 as LCM. It is I plus phi m minus 2 phi m by 2. So it is also I minus phi m by 2 in the second term. So check this simplification on the right hand side. In that simplification on the right hand side, you will get this final form. Cm by gamma h maximum. So check that carefully. Cm by gamma h maximum is equal to half into what is the right hand side? Cosecant I into secant phi m into sine I minus phi m by 2 into sine I minus phi m by 2. This is equal to sine square I minus phi m by 2. Now, according to trigonometry, sine square I minus phi m by 2 is half into 1 minus cos I minus phi m by 2. That is this sine square I minus phi m by 2, half into 1 minus cos I minus phi m by 2. Substitute that here. Now, in this right hand side, cosecant I 1 by sin I, secant phi m 1 by cos phi m, half into half 1 by 4. So this right hand side, due to the substitution, changes as Cm by gamma h maximum. Check that carefully. Cm by gamma h maximum is equal to 1 minus cos I minus phi m divided by 4. 1 by 2 into 1 by 2, 1 by 4 into sin I into cos phi m. Then from this equation, h maximum is equal to, simplify this equation for this maximum height, h maximum is equal to 4 cm, that is a mobilized quotient per unit length, into sin I into cos phi m divided by gamma into 1 minus cos I minus phi m, equation 8. This is the maximum height of the soil slope AB in that construction. In the right hand side, we know this I value, angle made by soil slope with horizontal. We know that I value, and we know this phi m value. Just now I explained this mobilized angle of friction phi m is equal to the angle of friction phi in the borrow area divided by factor of safety. This is known value. Gamma is also known value, and small cm in the forced triangle. In the forced triangle, we calculate the capital Cm value. Capital Cm is equal to the total mobilized torsion force that we can calculate in the forced triangle, divided capital Cm with the length of the failure surface AB, that AD, that is L. Then you will get the small cm. So all are known on the right hand side. By substituting them, we can calculate the maximum height of the soil slope. So this is the Kalman's equation to find out the maximum height of the soil slope. So just a minute, please. So this equation 8 gives the maximum height of the finite soil slope according to Kalman's procedure. So this is the Kalman's procedure to find out the maximum height of the soil slope of the finite soil slope AB. So number of times I repeated this Kalman's method because it is an important concept in unit 2. Number of times this Kalman's method is asked in the examinations. So please everyone prepare this Kalman's method. This is already given in the material. Prepare that Kalman's method. If anybody is having doubts, in that Kalman's method? Please ask me. Then after the Kalman's method, I am going to discuss the further concepts in Unit 2. The first one is stability analysis of finite side slopes. So this is an important one because most of the side slopes in civil engineering are the finite side slopes. The side slopes of embankment, the side slopes of earth dams, the side slopes of canals, all are finite side slopes. So in civil engineering, most of the side slopes we encounter are the finite side slopes. Before going to construct the structure, that is embankment or the canal or the earth dam, the civil engineer should thoroughly analyze the stability of the finite side slope. Stability means the identification of failure surface in that side slope. So please listen everyone. Stability means, what is the stability means? The stability means where is that failure of side slope happens? Where is the location of this failure surface in the side slope? So the stability analysis of finite side slopes is the identification, location of the failure surface in the side slope. We know that in finite side slopes, we have two types of failures. The finite side slopes basically are having two types of failures. One is the rotational failure. The next one is the rotational failure. The next one is the wedge failure. Although we have the combined failure, it is also there in the finite side slope, but most of the finite side slopes are subjected to these two types of failures. One is called the rotational failure. We know that the rotational failure happened along the curved failure surface. I already explained in the previous classes. The rotational failure happened in curved failure surface. Then the wedge failure happens in plane failure surface. I discussed these two types of failures already in the previous classes. Most of the failure surfaces, finite side slopes, are subjected to either the rotational failure or the wedge failure. In rotational failure, the failure surface is a curved surface. If the side is homogeneous, we call that failure surface, curved failure surface, as circle. If the soil is homogeneous in the embankment or earth dam, the failure surface of finite side slope is rotational failure. It is taken as the circular failure surface in the finite side slope. You know that the rotational failure is again having three types. One is the toe failure. One is called toe failure. Next one is called slope failure. Third one is called base failure. So like that, in the rotational failure, we have three types in finite side slope. One is the toe failure. If the curved failure surface in the rotational failure passing through the toe of the slope, this bottom post portion is called the toe. If the failure surface is passing through curved failure surface in the rotational failure is passing through the toe of the slope, that is called toe failure. Sometimes the curved failure surface is passing through the face of the slope like this. Here this curved failure surface passing through the face, this type of failure is called face failure. This is a rotational failure because the failure surface is a curved surface. It is a rotational failure, but here the curved failure surface is passing through the face of this side slope. So we call this rotational failure as face failure. The second one is toe failure. Just now I explained. If the curved failure surface passing through the toe of the side slope, we call this as toe failure. These two are the rotational failures. Apart from these two, Apart from these two, then the third type of rotational failure is base failure. That is important. In the base failure, the curved failure surface is passing like that. It is tangential to the hard stratum. Below this embankment, we have the hard stratum normally. In the base failure, the curved failure surface, it is also rotational failure. It is passing through the hard stratum tangential and it is coming out away from this toe. So this entire soil mass in the base failure subjected to failure. So like that, the rotational failures are three types. One is called the phase failure. One is called the phase failure. The second one is called the toe failure. Third one is called the base failure. In that base failure, please everyone listen. In this base failure, we have a factor called depth factor. The base failure of finite side slope is having a factor called depth factor. The depth factor in the rotational failure at base failure is defined as h plus d divided by h. This h is the, in this equation, that h is the height of this soil slope. This d is the depth of this hard stratum from this structure. The depth of the hard stratum from the bottom of the structure, that is called d. And in this base failure, we have that factor called depth factor. The depth factor of this base failure df is equal to h plus d divided by h. That ratio is called the depth factor of this base failure. Coming to the stability analysis of finite side slopes. The finite side slopes are existing in embankments, canals and earth dams. Most of the civil engineering structures are having these finite side slopes. Before going to construct the structure, either the embankment, earth dam or canal, the civil engineer should thoroughly check the stability of the finite side slope. Before going to analyze that stability, first of all, we should know what are the different failures of the finite side slopes. The finite side slopes are having basically two types of failures. One is called the rotational failure. Next one is called the wedge failure. In the Kalman's method, we discussed that wedge failure of the finite side slope. The next one is the rotational failure. In the rotational failure, just a minute please. In the rotational failure, again we have three types. In the rotational failure, the failure surface is a curved failure surface. If the soil is homogeneous, the curved failure surface is circle. In the rotational failure, we have three types of rotational failures. One is called phase failure, second one is called toe failure, third one is called base failure. In the phase failure, the curved failure surface passing through the face of the soil slope, and this portion of soil is subjected to failure. In the toe failure, the curved failure surface passing through toe of the soil slope, this portion of soil is subjected to failure. In the stability analysis, we must identify whether this failure of the soil slope is phase failure, toe failure or base failure. In the base failure, the failure surface is passing through the bottom of the toe, tangential to hard stratum, and this entire portion of soil is subjected to failure. In the base failure, we have a factor called the depth factor. The depth factor in base failure df is equal to h plus d divided by d. So that is the divided by h. That is the depth factor of this base failure. So like that, in this finite side slopes, we have this type of rotational failure. Now coming to the steps followed. The steps followed in this finite side slope. The steps followed in the stability analysis of the finite side slope. While analyzing the stability of finite side slope, this entire process is a graphical procedure. In the graph sheet, we analyze the stability of the finite side slope. First, we prepare the plan of the embankment, the plan of the earth dam, the plan of the canal slope is prepared on the graph sheet. After the preparation of the embankment or the earth dam on the graph sheet plan preparation, select a convenient failure surface in that plan by assuming either the wedge failure or the rotational failure. If it is rotational failure, assume a circle arc in that plan. Take that curved arc or the circular arc in the failure in the graph sheet on that plan of the structure. Then by considering that failure surface in that plan, consider the portion of the side wedge in the side slope and the failure surface. So coming to the procedure of stability analysis of finite side slope. In that stability analysis of finite side slopes, first prepare the plan in the graph sheet. Prepare the plan of embankment or the plan of earth dam or the plan of canal slope in the embankment in the graph sheet. After preparation of that plan in the graph sheet, consider a assumed failure surface in that plan. So consider one failure surface in the plan. That failure surface may be straight plane failure surface or arc of circle. Consider one arc of circle in the plan as failure surface. Then by considering the portion of soil between the finite side slope and the failure surface, find out all the forces acting in the side wedge. The side wedge is in between the side slope and the failure surface. So in this stability analysis, first we prepare just a minute, please, just a minute. So please listen. Sorry for the interruption, net problem. So please listen, everyone. The stability analysis of finite soil slope steps. So this entire procedure is a graphical procedure. So in that graphical procedure, on a graph sheet, this procedure is done by the civil engineer in the office. Whenever we are going for the construction of embankment, construction of earth dam, construction of canals, first we must check the stability of soil slope in those structures. Stability means the location of the failure surface in that soil slope. So what is that failure soil slope? Where is that failure soil slope of that finite soil slope? That location is called the stability analysis. So in that determination of the location of the failure surface in the finite soil slope, normally we follow this detailed procedure. First one is prepare that plan. Prepare that plan of the embankment or the earth dam or the canal on the graph sheet along with soil slopes. Once that plan is prepared, in that graph sheet, consider an assumed failure surface. Consider one failure surface in that plan. That failure surface, if it is rotational failure surface, it is curved surface. If it is a wedge failure surface, it is a plane surface. It is our assumption. Normally, most of the finite soil slopes are subjected to rotational failure, not the wedge failure. So, take one arc of circle as failure surface in the plan. After taking that failure surface, consider the soil portion in between the soil slope and that failure surface. Then find out all forces acting on that soil wedge. Consider all forces. We know that in the stability analysis of soil slope, some forces causing the failure, some forces preventing the failure. So by knowing the magnitude of all forces acting on that soil wedge, you can calculate the factor of safety. Factor of safety is equal to the magnitude of force resisting the failure divided by the magnitude of force causing the failure. Then repeat this process by considering the another failure surface in that graph sheet. Repeat this process by considering the another failure surface in the graph sheet. Consider the soil wedge in between the soil slope and the failure surface. Calculate all forces acting on the soil wedge, both the resisting force as well as the forces causing the failure. Find out the factor of safety. So repeat this process for a number of assumed failure surfaces in the graph sheet. Then among those different failure surfaces, for one failure surface, the factor of safety becomes a minimum. That is called the critical failure surface of the finite soil slope. In future, the soil slope is subjected to failure about that minimum factor of safety failure surface. So this is the procedure normally we adopted in the stability analysis of finite soil slopes. Then coming to the next concept, in this stability analysis of finite soil slope, we have four different methods. One is called friction circle method, second one is called Taylor's method, third one is called Swedish circle method, fourth one is called Bishop's method. By using these four methods, we can analyze the stability of the finite soil slopes of earth dams, canals, and also the embankments. So we have four different methods for the stability analysis of finite soil slopes. Friction circle method, the second one is Taylor's method, the third one is Swedish circle method, the fourth one is Bishop's method. Next class, I will explain the friction circle method of the stability analysis of finite soil slopes. Dear students, if anybody is having doubts regarding the Kalman's method or the rotational failure of finite soil slope or the steps followed in the stability analysis of finite soil slopes, please discuss with me. If you have any doubts regarding this discussion of today's class, you please contact me. Any doubts, students, from your side? If you have any doubts, you please ask me. Next class, I will start this friction circle method of stability analysis. Later on, we will discuss the remaining methods also. These four methods are used. These four methods are used in the stability of finite side slopes. Friction circle method, Taylor's method, Swedish circle method, and Bishop's method. Please remember, stability of finite side slopes is the determination of the failure surface in the finite side slope. So that location of failure surface in the side slope, finite side slope, is called the stability analysis of finite side slope.
Sir,
132.
sir,
చెప్పమ్మా.
finite soil slopes ki infinite soil slopes ki difference ఏంటి సార్?
Infinite side slopes are very long. There is no top, there is no base of the infinite side slope. Whereas for finite side slope, we have the top boundary. For example, if you take the earth dam or the embankment, we have the top of embankment, the bottom of the embankment, that is called base. The finite side slope is in between the top and the base of embankment. We have that limits for the finite side slope, and it is of only small length, maximum 10 meters or 20 meters length, or somewhat higher up to 50 meters. Whereas the infinite side slopes are very long. There is no top for the infinite side slope, there is no base for the infinite side slope. The example is the side slopes on the hills. Recently, I posted one picture in the third year group. From the hill, the side slope fails. It is falling on the road. Please, everyone, go through that picture. Recently, I posted last Sunday or last Saturday. I posted that
Yes, sir,
side
you
slope from the
posted,
hills.
sir.
That is infinite side slope. Side slope on the hills. Any doubts, please?